So yeah, today I'll just be presenting a little bit of work that I did last quarter. So in particular, I'll present an algorithm for globally optimal impulsive control with input magnitude constraints. Uh, and I'll show several demonstrations with relevance to spacecraft relative motion. Um, yeah, I guess I want to show like sort of the elegance and simplicity of this algorithm. So I'll try to keep this presentation short and sweet. So to get started, I'll start by giving a formal definition of impulsive control. So impulsive control typically involves input signals that act instantaneously over the state of the system. This means that the state changes occur instantaneously. So on the right here, you can see like a sort of basic example of an impulsive control scenario where you have an input signal that's driving the state of the system under some dynamics to some desired final location. Uh, Input control or impulsive control is typically very relevant for spacecraft, since the long time scales that are operated over and the high thrust that the spacecraft can achieve make it so that the problem can be modeled as an impulsive control problem, which is typically a bit easier to solve than the continuous time control cases. Obviously, there are caveats to this. This isn't always true. But with an impulsive control problem, you're solving you're optimizing over a discrete set of elements instead of a continuous signal, which makes these problems a little bit easier. So to get started, I'll just go through some of the usual approaches to approaching an impulsive control problem. So probably the most popularly used today is direct methods, which are very efficient and easy to implement and are very flexible in handling state constraints and input constraints. The main issue with these direct methods is that, they're numerical. You can oftentimes be solving a very large optimization problem, which isn't ideal. Analytical methods are very nice, they're efficient, and obviously the analytical properties make them very flexible and easy to implement. But they have limited use cases, and typically they can't consider a lot of those operational constraints. Indirect methods, in contrast to direct methods, apply optimality conditions directly to the continuous time version of the problem. So in this way, they're sort of rooted in this theoretical basis. But the problem is they're typically pretty difficult to implement and are not very flexible in handling constraints. I sort of consider the reachable set-based approach for impulsive control to be sort of a dual form of the indirect methods. So in this way, they also have that theoretical basis and suffer the similar weaknesses that indirect methods do. And then lastly, sometimes I see people apply particle swarm optimization a lot for impulsive control. I'm not sure if this is the best approach, though. So to dive into it a bit further, we can consider why not just use direct methods. The problem with direct methods is that they assign a discrete time grid to the solution space. So they discretize and then optimize instead of optimizing and then discretizing, which leads to inherent suboptimality because this discrete solution space does not capture the continuous effect that the impulsive controls can inhabit. So to capture the amount of input freedom necessary in an impulsive control problem usually leads to a very dense time grid. And this just means you have a lot of variables to solve for in an optimization problem. So it makes them much less practical to consider. There are several remedies to this problem. You can assign like a lower variable problem structure by introducing a time dilation parameter. But the problem is this leads to a nonlinear program, which can only be solved generally to local optimality and is generally non-convergent. So looking further, the reasons why you would maybe want to consider using a reachable set theory-based method or an indirect method is that these methods can capture the continuous behavior of the control space. And if formulated properly, the algorithms can actually achieve global optimality and global convergence, which is obviously very useful for our scenario. The issue with these methods, as I mentioned earlier, is the constraints can be difficult to handle, but hopefully we can address some of that in this presentation. So the contributions that I'll outline here in this presentation revolve around the extension of the indirect method framework to handle the input constraints at each maneuver. So this is a very practical constraint to consider in that at any given impulse, there is a limited amount of input actuation that you want to allow for. And other techniques and indirect methods for impulsive control have not yet demonstrated a capability of handling this sort of constraint. So in this talk, I'll introduce an algorithm that is able to handle these constraints, and I'll show that it achieves strong duality, which means that the resulting algorithm is globally optimal. The solution framework is globally convergent, and also there is a certificate of global optimality at the end of the optimization. So let's dive into the theory a little bit. I'll try not to go too much into the math, but if we consider the following optimal control problem, this is a pretty typical optimal control problem for spacecraft, where you have an input signal that you minimize the control effort. The control effort is quantified as the L2 norm of the input signal. And you want to satisfy the dynamic constraints over the time horizon and enforce boundary conditions for the initial and final times. And then typically you consider some sort of input signal that you want to use over this optimization problem. And for us, we're in particular going to consider this form of a control signal. I know it seems kind of weird, but this is actually a very important control constraint to place in order to achieve sort of the global optimality that we want. So you can see here, the control signal is made up of the sum of Dirac delta functions with some sort of maneuver direction. And we place a constraint that the sum of the maneuvers over some time window has to be less than or equal to 1. So this encapsulates the constraints that we want to consider for this specific problem. So what we do, if we go into it a bit further, is we can introduce, a set of time windows over which we want to consider impulsive maneuvers. And we say that the sum of the maneuvers over these time windows have to be less than or equal to 1. So you can see in this first window right here, this specific example, we have one impulsive maneuver and the magnitude is equal to 1, which is satisfying our constraint. In the second time window here, we have two impulsive maneuvers, but you can see that the sum of the impulsive maneuvers is less than 1, which means this also satisfies the constraint. And then in the rest of the time windows, we have no impulsive maneuvers or we have small impulsive maneuvers, which also satisfies the control signal that we are interested in considering. So this specific example right here is an instance of this control signal. So these time windows are chosen a priori, multiple. I think an important thing to consider is that multiple impulses can occur per window. That's sort of an important thing to have in order for this solution framework to work. So if we reformulate the problem, the objective becomes the sum of the magnitude of the impulses that we consider. And we assign this structure where we have a maneuver direction that is just a unit vector and some impulsive maneuver magnitudes that we say are less than or equal to 1. So to look at this problem a bit further, you can see that the problem has n variables, or n times nu plus 2 variables, which is a decent amount to consider. And it's actually non-convex because if we are trying to solve for the optimal times of the impulse maneuvers, then this constraint becomes non-convex. So this is obviously not ideal for online use. So to reformulate the problem, we can use a dual conversion, and we'll show that this actually makes the problem convex and therefore easy to solve. So if we formulate this partial Lagrangian, we have this dual problem. And we'll see that solving this dual problem will reveal this underlying structure of the problem that solving a primal problem that you would use maybe in like a direct method will not typically capture. And so we introduced this new term, this lambda f. This is like a Lagrangian multiplier. And this is actually equivalent to the terminal co-state of the continuous time dynamics, if you were familiar with that continuous time optimization theory. So going further, we can determine that the optimal impulse direction is given by something called a primer vector, which means that for all time, we have this analytical expression based on the terminal co-state of what the optimal direction to point your thrusters are. And then from that, we can determine what the optimal impulse times are. So the optimal times to actually fire your thrusters. And we can define this based on some switching function, which I give right here. And this actually is very similar to a switching function that you might define for a low thrust optimization problem, if you were familiar. So the best impulse times are given by the argument of infimum of this switching function over these time windows. And we can also determine well, we can't determine, but we define also the minimum switches that occur over those time windows. Generally, it's not possible to derive an expression for what these things are, but we'll see that when we numerically solve the problem, we can recover what these are upon completion. And then finally, we can look at the impulse magnitudes and see how the optimization problem simplifies based on the constraints on the impulse. So combining all of this, we arrive at this dual form of the problem. And importantly, this current form of the problem cannot be, readily solved, mostly because you have this term here that is not amenable to, analytical expressions or anything like that. So to reformulate, we can form a hypograph and then reformulate this constraint as a semi-infinite constraint. So essentially what we're saying is that some variable is less than the switching function for all time in this specific time window that we're considering. And if we add those to this expression here, then we recover the dual form of the problem, which is a semi-infinite problem. So just to go into the structure a bit more, I'll state one theorem regarding the problem structure of this dual problem. So this is a convex semi-infinite program. And the way we can see this is by noticing that the objective is affine with respect to the solution variables. And then we have this affine inequality constraint and a semi-infinite second order cone constraint. So you can think of this constraint actually, it might not seem convex at first glance, but essentially what you're doing is you're taking the intersection of an infinite amount of second order cones, which produces a convex constraint. So this is obviously a really useful property for this problem. This means that we converted the original primal problem, which was non-convex, into a convex problem. Another property that we can now state is the global optimality with respect to this dual problem. So we state that if the dual problem is solved to optimality and the resulting cost is bounded, then strong duality holds. This is a result of Slater's condition, but this is obviously a property that is super useful. This is something that cannot be attained by solving the primal on its own. And then lastly, we can state the feasibility. So another useful property is that if this problem is unbounded above, then that means that the primal problem is infeasible. So we can state that if you cannot solve this problem with a finite cost, then there does not exist a control signal that can drive your system from the initial condition to the final condition. So this is a super useful property that is not captured by other frameworks in which magnitude constraints are considered on the input, since generally you can reach any given state for any problem under that framework. And then lastly, we can see that we've drastically reduced the amount of variables that we need to solve for with this dual approach. And we've replaced those variables with less constraints as well, with the caveat that we are solving a problem with semi-infinite second-order cones. So now I'll just briefly go through the solution procedure for solving such a problem. So even though this is a convex optimization problem, it's not trivial to solve because of this semi-infinite constraint. And another thing is that solving this dual problem does not recover the optimal solution to the primal problem completely. So solving this dual problem, we will be able to obtain the optimal impulse times and the primer vectors, but we will not be able to solve for the magnitude of the resulting thrust profile. So to do that, we will need to solve a separate optimization problem upon completion of the semi-infinite program. So the procedures outlined here solve the semi-infinite program. The good thing about this is that you don't require an initial guess, unlike certain direct methods that are based on nonlinear programs. And also this semi-infinite program will emit global convergence. And then after that, you solve the feasibility problem of the primal problem. So we slightly reformulate the semi-infinite program to consider discrete times. So at every iteration of solving this optimization problem, we solve this problem sequentially, which means you can determine the global times over each time window and enforce a constraint at that time. So in that framework, we reduce the semi-infinite program to a finite program, which can be readily solved using any off-the-shelf convex optimization solver. And then once we solve that, we can solve this feasibility problem to recover the optimal impulse magnitudes. Now, an interesting property that we can leverage is we can take the sum of these impulse magnitudes, which is equivalent to the objective of the primal problem, and then we can compare it with the cost of the dual problem. And if you are familiar with optimization theory, you'll know that the dual problem is always less than or equal to the primal problem, which means that if there is no dual gap, as in the dual optimal objective is equal to the primal optimal objective, then that means you have achieved global optimality. So we can leverage this property by comparing the costs of these two optimization problems, and it gives a certificate. If this value is equal to 0 or close to 0, then we know that the resulting profile is globally optimal, which is great. So let's look at a basic example of this in practice. So I'll first consider a simple harmonic oscillator. So what we do is we set up our equations of motion and formulate our dynamical system. And then for this specific problem, I assigned 24 equally spaced time windows with a buffer time of pi/2. So that allows for this small buffer time between each impulse. And you can see the resulting profile in the phase space. So these red dots is where the impulses occur. And you can see that the optimization problem slowly drives the harmonic oscillator to the origin. So this is not like a trivial problem to solve, I would say. And we can actually compare it with the problem when we consider no input constraints. And you can see like this solution is blatantly violating any input constraint that we want to satisfy. So if we take a naive approach and not apply these input constraints, then you will not recover a solution that your system will be able to execute. So that's like sort of the beauty of this algorithm, is it allows us to incorporate that very practical constraint of ensuring that we are not producing impulses that our system might not be able to execute. So now let's look at a simple planar orbital reconfiguration problem. So you can see we start down here, and then over the sum of these impulses, we end up at our final desired state. And you can see the throttle profile here. We cap out at the first time window. And then at the second time window, we produce two impulses that are less than the total impulse requirement. And here we can see what the co-states look like over time. So an important thing is that this switching function must be, or it must be less than the cost given by the dual problem. So we can see that the optimal impulse locations are given by the points in this time window where the switching function is minimized. So in this first window, we have a lower bound at around -1, and that corresponds to a full throttle input. And you can see when we hit the switching function at 0 throttle, that produces an additional impulse that is somewhere between 0 and 1. And you can visualize what the switching function looks like here as well by plotting the co-states. So when this co-state trajectory is contained within the unit sphere, then that corresponds to no impulse. But when the co-states leave the unit sphere, that corresponds to a point where you would want to apply the throttle. So it seems you can see how we get this interesting structure by considering the primal form of the problem, which we wouldn't have otherwise been able to see by just simply solving the primal form. Another example we have here is in a long track to relative orbit. So additionally, you can see the same sort of behavior that was occurring in the previous example with the throttle and the switching function. So yeah, these are just some basic examples in Clohessy-Wiltshire equations. But if we look towards a relative orbital element example, I'm considering right here a transfer that I took from a visors example, in which you go from a standby orbit to a science orbit. And you can see that the throttle is spread out across like several hundred impulses, right? So if you imagine in like a convex optimization framework, or just solving the primal form of the problem, it would be extremely difficult to recover this optimal solution because of how many variables you would need to solve for. This is like several hundreds of impulses. And in addition, this improves upon some other indirect method or reachable set-based frameworks, in that we're enforcing this throttle constraint, which is highly practical for the visors mission. From what I understand, visors currently solves the unconstrained form of the optimization problem. And then it takes these impulses that are beyond the capability of the system and buffers them into multiple maneuvers. And in doing this process, you lose global optimality. So this specific framework is able to capture the original problem that we desire to solve with a globally optimal solution. So I think that is a very exciting result. And then lastly, we can look at the relative orbital elements. And we can see we maintain good RN separation over the course of the maneuver. And we also see that the EI vector separation is well maintained. So yeah, from the relative orbital elements perspective, the maneuver plan is also quite good. And then lastly, let's look at a starry result. That was something I'd also been working on last quarter. And in particular, the orbits that we are working with starry are fundamentally different than visors, because we desire to have a continuous observation for an inertial target. And this leads to a specific orbit for science that is inherently unsafe, right? You have 0 RN vector separation, RN vector separation, or EI vector separation. So this is obviously not ideal, and you want to ensure that you have a control framework that can generate highly accurate solutions and also does not violate the minimum RN constraint for too long. So we can see from this perspective that the RN separation actually decreases fairly linearly. And at the very end, we don't our RN separation is above like 20 meters for almost the entire transfer, which is good. This means we're not violating safety until the very moment that we need to violate safety. You can also see this with the EI vector separation here. So yeah, this is a very good result, I feel like, for a standby transfer. And you can see what this final orbit looks like at the very end as well, where you have these oscillations in the end direction. So yeah, no RN separation at the very end, but a very good maneuver plan nonetheless. I should also mention that these specific transfers took around 10 seconds to compute, which I think is like a pretty big improvement over other approaches, like a convex optimization approach. I seriously doubt you would be getting anything that close. So obviously more comparisons are needed to fully validate, but I think it's very promising nonetheless. So yeah, with that, I'll wrap up with some conclusions. So in this talk, I demonstrated a globally optimal, globally convergent algorithm for impulsive control of LTV systems with input magnitude constraints. And we showed how the algorithm functions for several relevant scenarios. And the algorithm happens to be highly efficient for these long duration maneuver plans that we are interested in. For future work, it would be nice to be able to generalize this approach to other input sets. So, for example, maybe L infinity norm would be interesting to look at. Another interesting thing that that I would like to look into is fusing both the feed forward and feedback control for optimal thrust allocation. So I believe in Visor's framework, they are applying an approach similar to this, but also applying feedback in the form of a stochastic model predictive control algorithm. I think it would be interesting to see if these two algorithms can be fused together in a framework in which you are guaranteeing some final covariance at the terminal state. In that way, you're fusing both the feed forward and feedback control and drastically simplifying the algorithmic approach that you are taking to controlling your spacecraft. So I think that could be a very exciting additional contribution as well. So yeah, that's pretty much it. Thank you guys.